In this video, we'll learn how to evaluate double integrals over rectangles. For this, we'll need a theorem, Fubini's theorem. Which is applicable to continuous functions. There is a more general version of this theorem, but we'll only need this weaker version, which is for continuous functions, and it states that if f of x and y is continuous over the closed domain that is a rectangle AB cross CD, then its double integral, the double integral of f over R, can be evaluated, computed using iterated integrals, meaning that we first integrate with respect to y, with y going from c to d. This way we get a function of x only, which we integrate with respect to x as x goes from a to b. So this is one way of computing this double integral. Another way is to do it in the other order. First integrate f of x and y with respect to x, treating y as a constant for the moment. X changes from a to b. This will give us a function of y, which then we can integrate with respect to y as y changes from c to d. So the point of this theorem is that this double integral exists and can be evaluated as either one of these iterated integrals. Okay, so let's now look at an example. So take the function f of x and y, that is x squared times y, over the rectangle that is the Cartesian product of the closed intervals 0 to 3 and 1 to 2. This function is clearly continuous over this rectangle, so Fubini's theorem applies, and use Fubini's theorems and these iterated integrals to evaluate the double integral of f over R. Pause the video and input your answers below. Okay, I hope you paused it and found that when you first integrate with respect to y this function and treat x as a constant, so we first evaluate this inner integral, we are going to get, for the antiderivative of this function x squared times y with respect to y, we'll get x squared, that's just a constant multiple with respect to y, times y squared over 2. That we could add to this an additive constant, but since we are evaluating a definite integral, we can omit that plus c. So as y changes from 1 to 2. So when we evaluate this inner integral, we will get just a function of x. So what is this expression here? We take x squared and multiply it by y squared over 2 as x varies from 1 to 2. So that's x squared times 2 squared over 2 minus x squared times 1 squared over 2. So this is just the Newton-Leibniz theorem we are applying here, and we then integrate with respect to x. So what we have here in the parentheses is of course 4x squared minus a half x squared. So that's this is 2x squared minus a half x squared. So that's 3/2 x squared. We integrate that with respect to x. So the antiderivative of that will be 3/2 times x cubed over 3. As x changes from 0 to 3, we get 3/2 times, well, we can simplify it by 3, so we get 3 cubed over 2, so that's 27 over 2, and the left endpoint of this interval gives us the value 0, so we subtract 0 from this. So 27 over 2 is the value of this double integral. Let's compute the iterated integrals in the other order. First integrating x squared times y with respect to x, and then the result integrate that with respect to y. So what we get for this inner integral is x cubed over 3 times y. We treat y as a constant for the moment, and of course x changes from 0 to 3. So when we evaluate this expression, we get 3 cubed over 3 times y minus 0 cubed over 3 times y. Y goes from 1 to 2. Then we integrate this function with respect to y. So what is this function? Well, it's 27 over 3, that's 9y, and we subtract 0, so it's only 9y integrated with respect to y, giving us 9 y squared over 2 as y changes from 1 to 2. So what that gives us is 9 times 2 squared over 2, that's 2, minus 9 times 1 squared over 2, that's a half, so 9 times 3 halves, that's 9 times 3 over 2, that's 27 over 2. Okay. Finally, as an application of double integrals, let me mention average values. So we can use double integrals over rectangles to compute the average value of a function of two variables. So if we have a function of two variables, the average value of that function over a rectangle will be the area of the reciprocal of the area of the rectangle times the double integral of f over that rectangle. Okay, so for example, if we consider the previous function over this rectangle, its average value will be, well, the double integral was found to be 27 over 2, and the area of this rectangle is of course 3 times 1, so 3. One side is of length 3, the other side is of length 1, so that's 3. So for the average value we get 9 over 2 for this function. Alright, I hope you enjoyed this video, and I'll see you in the next one.